Okay, so let's get started. I'm very happy to introduce Rachel Holladay. Rachel obtained her undergrad degree from Carnegie Mellon University in computer science and robotics. Now she is a PhD student at MIT. She's in 2 labs, and I'm sure that she will tell us about that. Rachel, please. And she will talk about constraints and planning for forceful robotic manipulation. Please, Rachel.
Thanks, Dan. Yes, so as Dan mentioned, I'm in 2 labs, so this is work done in collaboration with both of my advisors, Tomas Lozano Perez and Alberto Rodriguez. We're all at MIT. So generally speaking, I am interested in constrained motion planning and contact-rich manipulation. And the bulk of my graduate work has been focused in on a specific category of manipulation tasks that we call forceful manipulation. We categorize forceful manipulation as tasks where exerting substantial forces is necessary to complete the task. And while all actions that involve contact, kind of by definition, involve forces, we focus on tasks where generating and transmitting forces is a limiting factor that has to be reasoned over and planned for. So interested in forceful manipulation, another aspect of these tasks, which it's a good thing we got the box to move, is that a critical aspect of these tasks is that we are interested in tasks that involve multiple steps. So we aren't just interested in the isolated task of, how do I twist that nut on the bolt, but the entire process that surrounds it. Do I have enough force to twist that with my fingers, or do I have to go grasp the tool? And if I have to go grasp the tool, what is the grasp that I use? How do I move in order to bring that tool in contact? And how could I accomplish this task kind of in a variety of environments? So how are we going to approach this? We're going to start by assuming that we have our forceful manipulation task specified as a fixed sequence of steps. And our goal is going to be to find the parameters of those steps. And we're going to frame this as a constraint satisfaction problem where those parameters are decision variables. And we're going to walk through the constraints that impact our space of solutions, building up this constraint graph. And in particular, we're going to focus on the constraints that are related to forces, unsurprisingly, and discussing them within the concept that we call a forceful kinematic chain. And this will get us pretty far. We're going to show a sequence of tool use tasks, for example, using the claw of a hammer to pull out a nail. But this won't critically get us the entire way. And that's because that initial requirement of needing a fixed sequence of steps to accomplish this task is pretty limiting. And so we'll show how if we define our steps more generally as a series of operators, that this removes that constraint to have a fixed sequence of steps provided and enables instead the robot to be able to plan over the sequences, effectively generating and evaluating its own constraint graphs instead of us defining them by hand. And for the second half of the talk, the task I'm going to use is a robot opening a child-proof bottle, specifically one that forces you to do a push twist. And by kind of taking this more general view with planning, we're going to enable our robot to kind of find, as the videos show, a diverse set of solutions. So in the first half, we're going to borrow heavily from mechanics. And then in the second half to do planning, we're going to borrow heavily from area known as task and motion planning, along with motion planning and control aspects spread throughout. My hope is to go through each of these 2 pieces. People should interrupt me in between with questions, then we'll go through questions. And if we have time at the end, I actually want to talk a little bit about the more algorithmic bits of task and motion planning again if we have time. Are there questions so far before we kind of dive in?
Nope.
Okay, cool. Before we fully dive in, I do want to mention previous work that's been done. So there's been work by Mehmet Dover's group, where they get a robot to reason over how to fixture in reaction to a human exerting forces. And while we borrow some terminology from their group, we'll see in the second half that we're actually going to have the robot be the agent that both fixtures against and is exerting forces. There's no human in the scene. There was some great work by Peter Allen's group in the 90s where they look at that same task of opening a childproof bottle. Their medicine bottle has a skull and crossbones on it, so I don't super know what's happening there. But they formalize it using a finite state machine, which again kind of is similar to what we'll do in the first half, where we have a fixed sequence of steps, but we're going to generalize to planning, as we said before. And then if we talk about planning multi-step tasks while reasoning over forces, the most related work is out of Mark Toussaint's group. They use an optimization-based method while we use a sample-based method. They are able to handle dynamic actions. For example, here you see throwing, but they do have a more limited definition of forces that doesn't involve them reasoning over torque. So there are various trade-offs between our work and theirs. Speaking of forces and torques, there is one distinction that I must make in all of my talks, which is that we have wrenches and wrenches. So we have, in the context of this work, both a tool and a 60 force torque. So I'm going to call the tool generally a spanner. And when I say wrench, I'm generally referring to the 60 force torque vector. Okay, so those are our preliminaries. Let's dive into our constraints. So as I mentioned, we're going to use this illustrative task of we want a robot to use a hammer, the claw of a hammer, to pull a nail out from a block of wood. And for now, although as I mentioned, we'll relax this later, we're going to assume that we're given a fixed sequence of steps in order to accomplish this task. So we might assume that in order to do this, we're going to first grasp the hammer. We're then going to bring it in contact with the environment, in this case, the nail. Then we're going to pull the nail out, making this arc in motion to pull it out. This is kind of the forceful manipulation aspect. And then once we've accomplished this part of the task, we may imagine wanting to put our tool back where we found it. And the benefit of kind of breaking up a task like this into the various steps is that it identifies the pieces that we need to solve for in order to complete this task. So that if we wanted our robot to do this, the robot has to select a grasp on its tool. That's what's highlighted in green. It has to select kind of what is the relative pose when I make contact with the environment, that's given in blue. And it also has to find the series of paths to accomplish this task, and that's what's highlighted in red. So the things that the robot needs to solve for effectively are decision variables, and they're high dimensional continuous decision variables. And each of these decision variables has a series of constraints, some of which are force related, some of which are motion related, and all of these constraints and decision variables between them have dependencies. And so what we're going to do is kind of map out what those decision variables, constraints, and dependencies are. Specifically, we're going to build up our constraint graph. And so the decision variables, the things we needed to solve for, the graphs, the poses, the paths, become nodes within our graph, and we're going to iteratively build up this graph. First thing we're going to focus in on is the force-related things. Always focus on the forces. And so the forces come into play when we actually do that motion of pulling the nail up using the claw of our hammer. So how do we do this? So if we zoom in a little bit, we can imagine that we can treat our entire system, which in this case is the robot arm and its grasp on the tool, and the tool as one kinematic chain. Now, this kinematic chain is made up of a series of joints, some of which are robot joints and some of which are frictional joints, such as in this case, the grasp on the tool. For now, we're going to assume that the thing that we are acting on is rigidly mounted to the world. In this case, you can see this 80-20 rigidly mounted. We'll make this assumption for now. Later on in the talk, we will relax that. So we have this kinematic chain, and the constraint that we want to check in order to be able to accomplish this task is that when a robot is exerting this wrench, when it's accomplishing this action, we want to ensure that the kinematic chain that is formed by these series of joints is maintained. That is to say, in the face of the exerted wrench, each of the joints within this chain can resist that wrench. Another way to think about it is that the robot is strong enough to complete this forceful action. So in order to check this, for each joint, we're going to mathematically model what is the set of forces that that joint can resist. And if every joint is strong enough, And then we'll say the entire chain is strong enough, or I'll say that it's stable, not in the traditional control sense, but we'll just say that the joint is stable. And therefore, if that is true, then our constraint is satisfied. So what are the different joints within our chain? So we'll start off with the robot joints. What does it mean for a robot joint to be stable? So for each robot joint, there is a limit to how much torque can be experienced by the joint, and that is the robot's torque limits. If the robot experiences more torque at that joint than it's past its limit, then you hit what's called a torque fault. Normally the robot stops moving and makes a very sad noise. You have to reboot. So what it would mean for that joint to not be maintained or for that joint to break is for a robot to hit a torque limit. So how do we quantify how much these particular joints can take? So what we need to do is we need to transform the wrench experienced during our task into the torque experienced at our joint. And do this, use a mathematical operator called the Manipulator Jacobian. There's a brief review. The forward kinematics of a robot are a relation that maps the robot's joint configurations, the robot's Q, into the position of the end effector or the hand. And if you differentiate this relationship with respect to time, you get the robot's Manipulator Jacobian. And the Manipulator Jacobian maps the velocities of the end effector into velocities at the joints. Now, beautifully, I think, if you take the transpose of that relationship, the transpose of the Manipulator Jacobian, which is what's written up on the screen, that actually maps wrenches at the end effector to torques experienced at the joint, which is the exact thing that we need. I also note that the Manipulator Jacobian is configuration dependent. It is a function of our robot's joint angles. And intuitively, this makes sense because if you were to think about your own arm, you might imagine that at different configurations for your arm can resist or exert more forces. And so our configuration dependent Jacobian captures that. So once we have, we can take the wrench experienced by our task, we can use our Manipulator Jacobian to transform it into torque experienced at the joints. And then to evaluate if our joint is strong enough, we basically compare against, are we within our robot's torque limits? And we can do this for all of our the joints in our kinematic chain. So that covers for robot joints. The other kind of joint that we mentioned is that we have frictional joints. And these are specifically, in this case, formed by the grasp of our robot on our tool. So how do we quantify how strong this joint is? What is the set of wrenches that this joint can resist? To answer this, we're going to zoom in to what type of contact that we're making. So in my work, I use primarily what's called parallel jaw grippers that can only move in one direction. And for our joint to not be maintained, for our joint to break in this case, that would mean that our grasp on the object slips, that our object moves relative to our hand and that we do not have a fixed grasp. So what are the possible motions given a parallel jaw gripper? So I'm going to argue if we close our robot's hands in 3 dimensions, our object cannot move. And that is due to kinematics of non-penetration limits. That if you were to visualize for a minute closing the fingers, that for instance, the object cannot move to the left because to do so would involve the object moving through the fingers. And so we're going to assume that in these 3 dimensions that because our hand is rigid, we can resist an infinite amount of force and torque. This assumption is held for me all but once when our robot fingers cracked in 2 and we had to reprint them. But otherwise, we're going to assume that our joints are rigid and we can exist infinite force in these 3 dimensions. What about the other 3 dimensions? So in the other 3 dimensions, it actually is valid that our object can move within our grasp. And the thing that is preventing that motion is friction. So the question then becomes, how much friction is provided by our grasp in order to counteract and prevent that motion? In order to capture how much friction is provided by our grasp, that's quantified by something called the limit surface. And I'll say that because of our parallel jaw gripper, we are dealing with what's considered a planar grasp because we only have motion in 3 dimensions. And within our work, we construct the limit surface in 2 different ways, either using the ellipsoidal approximation or the generalized friction cone. Which one we use is dependent on the type of grasp that is being made. So to get into a little bit of the mechanics weeds, as well as to kind of better understand what the limit surface is, we're going to walk through the ellipsoidal approximation, how we actually construct and check that. So limit surface defines the set of all possible friction wrenches that our contact can offer. And so one way to think about this is that if the external wrench that we experience lies within that set, then the frictional forces can resist the external wrench. Effectively, our grasp won't move. You know, in the battle of our external wrench versus our friction, friction wins. If the external wrench lies outside of the boundary, then basically our grasp will slip because our external wrench overpowers the friction that's provided. Now, actually, the way the grasp slips is well characterized, but we're not going to use that specifically in this work. And we're just going to check, does our grasp slip or not, which is, is our grasp maintained or not? So if we have circular patch contact and uniform pressure distribution, then there's a compact and efficient construction of the limit surface, which is specifically known as the ellipsoidal approximation. I've cheated the axes a little bit here, but it is ellipse as drawn. And so this ellipse captures the set of frictional wrenches that our contact support offers. We're doing this, as I mentioned, it's in 3D. We have a planar grasp. And so given that we're operating in 3 dimensions, our ellipse is defined by this matrix A. And this matrix A is a function of a couple of things. There's the friction coefficient mu, there's our grasping force N, there's the radius of our contact R, and then there's a integration constant C. And we know our grasping radius because that's a function of our finger. We can control our grasping force. And we have a conservative estimate for our friction coefficient. It's an assumption within the work. So from that, we can construct our matrix A, which gives our construction of our ellipsoidal limit surface. So that's some math. Let's walk through how that is actually used in practice. So we assume that we have some notion of what is our experienced wrench throughout the task. We can use the adjoint transform to transform that from our task definition into our contact frame. We assume in 3 dimensions, as we mentioned, that we can resist infinite force. And so we take our 3-dimensional slice of what is being reasoned over for friction. And we can see in this drawing, in this case, our experienced wrench lies outside the boundary of our limit surface, which in this case corresponds to, we can kind of verify it through math, that this is a bad grasp because we do not have enough frictional support. And if we were to do this grasp, our grasp would slip, which would correspond to breaking our kinematic chain. So in this case, what we'd want to do is select a different grasp. You can imagine if we were to transform this into the contact frame and take the 3D slice. In this case, when we plot within our limit surface, this wrench lies within the set of boundaries that we can resist. And so this, if we check back through our ellipsoidal equation, that this is a valid grasp. This is a grasp that we can maintain. So bringing this back a level, we can check whether our frictional joints are maintained in our forceful kinematic chain by a combination of using kinematics assumptions, as well as checking for frictional limits, specifically using the limit surface. And so once we have this, for each of the types of joints within our chain, we have a way to check whether that joint is maintained and therefore whether our forceful kinematic chain is stabilized. I'll take a minute. Are there questions so far that come up? Okay, I will take that silence as a no. Okay, so we have our forceful kinematic chain. And if we go back up one more layer, this is now a constraint on our decision variables. And how does it come into play? It comes in 2 places, specifically that we now need to make sure that the grasp that we select early on is stable, and that while we are executing that action, remembering that that check is configuration dependent, we want to check that every configuration along that path is also stable. So this captures the force constraints. There are a couple of motion constraints that I'll go through fairly quickly. A major one is that we want that motion to be stable, but there's a question of what is that motion. And you can imagine for the hammering task, the type of motion that we want to achieve is that we want to basically do an arcing motion with our hammer. And so the way that we quantify this is that as a function of where we place our tool relative to, in this case, our nail, we have a series of waypoints defined specifically in task space that define the motion that we want to achieve. Again, for the hammering task, you can imagine it's kind of this arcing motion. Given our grasp relation, we can transform the path from our tool into a path of our end effector. But our end effector is not floating in space, it's connected to a robot. And so our problem becomes, how do we generate a path for our robot's joint angles that enables it to follow a path for the end effector, which then enables the tool to follow the desired path defined for the task. And so we quantify this constraint. I'm going to call it basically our path following constraint. And because it's a function of the grasp and the tool location, there are constraints added, reachability constraints added for both of those. In addition to all of this, for kind of everything we do, we want all the paths that we generate to be collision free. So this actually defines all of our force and motion constraint related constraints on our different decision variables. But we're not done just yet. So now we need to quantify what are the dependencies and relationships between these decision variables. And in walking through that, I'm actually going to very briefly explain how we solve this constraint satisfaction problem. And it is perhaps the simplest way you could solve a constraint satisfaction problem, because we effectively use rejection sampling. We're going to start off by, we have some grasp set and some tool set, and we're going to do rejection sampling in order to generate, in this case, our G and our T. Once we have those defined, those are inputs into our method for finding a path that both follows and is stable. And actually, to generate that, we use a special graph-based planar that uses the Frictional distance to capture that notion of following. And this was actually work done by one of my favorite people, Oren Salzman. And unfortunately, I won't be talking about that, but Oren and I would be happy to talk about it at length at some other point. And so we use a special planar for that. But otherwise, once we have this solved and once we have our grasp, you can imagine we can now solve for our path to the grasp. For anything besides that path following, it's not terribly important, but we use a bidirectional RRT for just our generic collision-free planning. And essentially, once we have these variables figured out, we have enough information to solve for all of the connecting pieces. And so what we do for this, again, to summarize, is that we basically sample for the different values. And if at any point we fail to find a sample, i.e. we fail to select a grasp or one of our planners fails, we basically start back from the end. It's a very simple way to do our constraint satisfactions. We just kind of keep sampling through this decision graph until we find a valid solution. And putting all of this together, we can now solve a series of tool use problems. Basically applied this same framework to 4 tasks, the first of which is this hammer pulling that's been our illustrative example throughout. In addition, there are 3 other tasks, one of which is using a screwdriver to kind of twist a nut. There's, we'll label it cutting. I think more accurate would be to say we are notching wood with a knife. And then the 4th one is that we are using a spanner to twist a nut on a bolt. And these all use kind of that same constraint graph formulation and that same set of constraints that we just walked through.
Rachel, how real life are these examples? Or did you make special room for the mail or anything? Can you tell us?
Yeah, so I think there are a couple of simplifying assumptions. So you'll notice that each of these tools were printed, and they're all printed to have the same handle, and specifically a rectangular handle, that if you were to like go into your shop, I'm going to guess that your screwdriver is probably more of a cylinder handle instead of a nice rectangular prism. And so that is the assumption we make because it makes that contact modeling easier, that we have a planar grasp.
Fair enough.
So that's an example of one where it's like, how do we make this more robot friendly instead of human friendly? There is also an assumption, which is true here and true in most of my work, that we assume we know the locations of everything. There's no vision algorithm that's running. We have told the robot where everything is in the scene. Yes, I'm sure I could talk about all of the details of the dirty laundry.
Okay.
for a long time, but I think those are two pretty major assumptions.
No, they sound very good. I don't want to interrupt you too much now, but perhaps later. I was more concerned with how deep the nail is stuck in the piece of whatever it is, and so on. The other assumptions sound very reasonable to me.
Yeah. Yeah, there are, I think in this case, as the video shows, we kind of twist the nut for a fixed period of time. And if you actually wanted to fully tighten a nut, or if you wanted to fully drive in that screw, you would need to, I think, lean into kind of either a closed loop system or this notion of generalized planning, where you're basically repeating an action over and over again until you finish. So like, you would need to do that if you wanted to fully tighten that bolt. In this case, we're only twisting it.
Okay.
So something, and pardon the pun, that I want to hammer home is that these constraints actually do matter, and you do have to reason over them. And to illustrate that, you can imagine what if you listened to all this and said, I don't want to care about these constraints. And so specifically, let's say you were to turn off the torque check, verifying whether it's a forceful kinematic chain, and if you were to plan with that check commented out. Here we color the joints based off their proximity to a torque limit. And you see that like the robot predicts that, hey, it hits a torque limit. And if you were to run this on the actual robot, sure enough, and I've muted it, but it makes a rather unhappy noise and hits a torque fault. So if you don't reason over these constraints, you actually cannot complete the task. And so in this case, what you would want to do is ask the robot to plan again, this time respecting those constraints, and makes a different series of choices such that it's actually within all of its limits and it is a valid forceful kinematic chain. And if we run again, now we're able to successfully complete the task because we've cared about our constraints. Okay. So returning back to this constraint graph, this constraint graph is nice in that it actually captures our entire problem. But as a reminder, we are doing this in the context that we were given a fixed sequence of actions, that we told the robot, do this, do this, do this. And from that, we then identified our variables and our constraints, and then by hand, we kind of walked through how do we generate this constraint graph. But this is limited, and this is the limitation that I care the most about, because the robot has no flexibility in how it actually completes the task. We've prescribed that you must do it this way, and therefore it's not going to be able to generalize to any different kinds of environments. And so in order to actually facilitate generality for multi-step tasks, I want my robot to plan its own sequence of actions. And this is going to move us into the second half. And so the robot needs now, instead of me doing it for it, it needs to be able to generate and evaluate those constraint networks by itself. And before we get to the pill bottle example, I want to think about what would this take? What would our robot need to do in the context of our hammering task that we've kind of worked to understand so well? So towards the beginning, I kind of laid out these are the steps that our robot is going to do to accomplish this task. And I was actually pretty vague in how I defined this. I kind of said these are steps, and we're not going to formalize this at all. But now I want to take I want to formalize what each of these are. Instead of saying that these are stages, I want to formalize them in something called operators. And we'll deal with toy operators for now, but they'll get our point across. And so what is an operator? An operator is effectively a parameterized controller, that we have some controller that the robot is running, and that controller has various parameters. Our controller is defined and described by there's a set of preconditions, which are what are things needed to be true in order to execute that controller, and then also by effects, which is after we run that resulting controller, what are the effects on our state? That's our definition for an operator. You can imagine maybe for that first stage that we had, that our operators is move to grasp, where we're executing some kind of position controller, and our parameters are what is that path and what is the grasp. And we have some preconditions about things being collision free. And the effect once we've run this controller is that we end up at the grasp that we want. Okay, we've written down what we already know. What was the point of this? What's powerful about this is that if we formalize it as an operator, that this operator actually defines a piece of our constraint graph. That the variables of our constraint graph are now the parameters of our controller, and the constraints that we have come up as the preconditions and effects defined within our operator. And that the preconditions and effects also define what are valid sequence of operators. Like how can we actually compose each of these pieces? Because the effects on step I have to line up with the preconditions on step I+1. And so what this enables us to do is if we define a set of operators, that if we have what's called a plan skeleton, which is the sequence of operators that our robot wants to do, that automatically defines what our constraint graph network is. So we no longer have to like sit here and define it by hand. Our robot now, if it generates a plan skeleton, it can automatically generate what is the resulting constraint network, and then evaluate to see if there's a valid solution for it. And this is what is going to enable us to do planning in order for the robot to generate different sequences for different environments. So to really see this in action, I'm actually going to move to what I would consider a more interesting task, in the sense that it's a task that has a lot more different ways to solve it. We'll walk through how do we define this task, and then what are the operators, and then we'll bring back how we use this idea of planning in order to generate kind of the video that I showed earlier. But I want to break for a minute if there are questions so far. No, okay. So I want to define our task, which is now we want to open a push to twist child-proof bottle, which I actually don't know if it's as ubiquitous in y'all's medicine cabinets as ours. I hope that it is. So in order to open this kind of medicine bottle, what you need to do is both push down on the cap while twisting it. Apparently that makes it childproof. In addition to kind of exerting this push and this twist, we're also going to insist that if our robot is exerting a wrench on our object, that it needs to secure or fixture the bottle. Basically, if you're exerting a force, you need to hold the object in place. In the first half of the talk, we kind of assumed that our objects were rigidly attached to the world. We are removing that assumption. Now it is the robot's responsibility to handle that. So our goal is simply that if you must do this push twist while securing the bottle, and then you can remove the cap. That is the task that we're focused in on. And the really cool thing about it is there is a wide range of methods that our robot could use to accomplish this task. And here are kind of snapshots of 3 different ways you could solve it. So you might imagine on the leftmost side that the robot could use the contact between the bottle and the table in order to fixture it, and then kind of grasp on the cap and use that to push twist. You might imagine in some scenarios that maybe that contact between the table and the bottle is insufficient, and so the robot now wants to fixture the bottle using a vise, and so the robot must first pick up the bottle, place it in the vise, and then in the middle picture, it's going to use its fingers in order to exert that push twist. Or maybe you might imagine maybe the vise is kind of out of the way and it's hard for the robot to get to, and so instead what it's going to do is it's going to pick up the bottle and put it on a high friction surface, which is the red mat shown, and it's going to pick up and use a tool in order to exert enough force to do that push twist. So there's a wide range of ways that the robot could solve this one task, and you can imagine that even for each of these 3 different strategies, that this involves a different sequence of actions and therefore generates a different constraint graph that the robot has to reason over. And so we want our robot to be able to plan for any of these possible options. And so in order to generate this, what are the operators that our robot is going to have access to? Now, I'd argue there's kind of a general set of operators that are probably useful for any task. In our toy example, we had move to grasp, but in practice, we actually break that up into separately having a move operator, which is I want the robot to move from one location to another. There's a slight variant of that called move holding, where the robot is moving holding an object. We also want operators where the robot can pick up an object or place down an object. So these are kind of general things that we want, right? We want our robot to be able to move and to pick and to place. But there's certain operators that we need to define specifically for the task of like, how do we get the robot to exert that push twist, or how do we get a robot to fixture the bottle in place before doing that? So let's first focus on how do we get our robot to do that push twist? Like, what are the operators that enable that? So within our work, we actually define 4 different ways that the robot could choose between. It can use its fingers, as I mentioned, by grasping the cap first. It could push down with its fingers, it could push down with its palm, or it could grasp a tool and then push down with the surface of that tool. I'm not going to go through the gory details of how we define each of these 4, but there are 2 things that I do want to highlight. One is that you can imagine each of these different configurations defines a different forceful kinematic chain. And that they each have within them, in addition to the robot joints, they're now a series of frictional joints. And actually, the way we define them, all of our frictional joints are actually still planar frictional joints. We can use kind of all of our mechanics that we discussed in the first half of the talk. And a precondition for executing any one of these controllers is that the forceful kinematic chain that is constructed is stable. So that is where our forceful kinematic chain check comes in. It comes in as a precondition for executing any one of these actions. That's the first thing. The second thing is, we want to do this push twist operation. And there's a question of what is the controller that is actually running? If I've set an operator as a parameterized controller, what controller am I running in order to do this? In order to answer this, we're going to do a bit of a controls, dive into controls. So let's say that I have a very simple robot. And the reason why I'm using a simple robot will be clear in a few seconds. If we have a robot and it's moving just within free space, then it can move in any direction, but it cannot exert force in any of those directions, because in no directions is it making contact. That's on one extreme. On the other extreme, you can imagine we have a robot encased in a block of concrete. This is why I use a simple robot, because it's surprisingly hard to find a picture of a robot encased in a block of concrete. But if you have a robot that's encased in a block of concrete, it cannot move in any direction, poor little robot, but it can exert force in every direction. It's in contact in every direction. So these are kind of 2 ends of the spectrum. And on one side, if we're in free space, this is where position control really shines, because you're just controlling positions. It has no ability to deal with force disturbances. And on the other end of the spectrum, this is where force control really shines. Arguably, force control is useful in cases where you're not encased with concrete. Force control is useful if you're in contact. But these are the 2 ends of the spectrum, and arguably we are somewhere in between. What we want to do is exert motion in some directions and force in some directions. And there is a control method called hybrid position force control, which would be very appropriate in this case. But we're actually going to do something a little bit simpler, which is that we're going to use a form of compliant control called Cartesian impedance control. So impedance control, just kind of as a brief reminder / overview, is that rather than controlling position or controlling a force, the 2 ends of our spectrum, is that we're going to regulate the relationship between position and force. The way it's usually described is that we're going to ask our robot to render the behavior of a mass spring damper. Everything through a mass spring damper kind of regulates the relationship between position and force. This is fantastic work done by Neville Hogan in the 80s. And so that's generally impedance control. What we are specifically doing is Cartesian impedance control. So in order to specify that for our controller, we need to specify what is the stiffness kind of that mass spring damper. In general, it's a stiffness matrix, but we're actually only going to be specifying the diagonal, which is what is the stiffness in each of our Cartesian directions. In addition to specifying a stiffness, you need to specify a damper. We specifically are going to set our damping such that we are critically damped, which means our damping values are simply a function of our stiffness. And then because it's Cartesian impedance control, we need to specify what is the set point to our controller, what is the position that it's regulating around. And because it's Cartesian, that set point is going to be a position and orientation opposed in SE3. And so our controller, what we need to specify to it is a stiffness, a damping, and a set point. So given that we have this control methodology, how do we use that to actually accomplish our goal of exerting a push twist? Let's start with the pushing part first. So let's say that we have our robot from before, and it's in contact with the ground. If we take our commanded set point, the position that it's regulating against, and we actually put that into the ground, we have some offset. What's going to happen is that our robot is going to try to achieve that set point. And in doing so, it's going to exert against the ground, compressing that spring, and therefore exerting a force. So that is what is creating the pushing action. Now I'm saying the robot acts like a mass spring damper, and it would be very fair of you to say like, okay, yeah, the robot acts like a mass spring damper, but like, is it actually? And for the robot that we're using, which is the Franca Amica Panda, perhaps shockingly, it really does act like a mass spring damper. We did some back of the envelope measurements and calculations, and if you take a certain stiffness and you plot the difference in like the offset in Z versus the force commanded, it's an amazingly, like Hooke's law comes out nearly directly, which is, I guess, a credit to the engineering of this robot. So the nice thing about this is if we heuristically pick a stiffness and I say, I want to exert this much force, then I can directly, basically through a linear relationship, say, this is the offset in Z that you should command in order to exert that force. Okay, so that tells us how do we get the pushing aspect of our push twist. Now we need to do the twisting aspect, and that basically corresponds to we need to generate a series of set points that move us around in that twisting motion in a circle. And so bringing this all back, in order to exert that push twist, we are using a Cartesian impedance controller where what we specify to the controller, or what the planner selects as the parameters to that controller is that series of set points, you know, the motion around combined with the offset and the stiffness in Cartesian space. And so this is the controller that is used for all 4 of our push twist operations. You can imagine each of them have slightly different parameters, but it's the same kind of core controller used for all of them. And so this is a set of operators that we can add to our list in order to exert the push twist. The other thing that our robot needs to do throughout this task is that it needs to fixture the bottle. And so we actually define there are 3 ways that the robot can fixture the bottle. One is that if you have a second robot, you can use that second robot to basically hold the bottle in place while the first robot is exerting this push twist. The grasp that that second robot is doing has to be stable. So we use all of our mechanics from before, but we already have a way to grasp, so that doesn't actually add an operator. The second way that we can fixture the bottle, as I mentioned before, is that we can use a vise. I will say, in our case, our vise is basically a shunt hand mounted to the environment. And so in order to use this fixturing method, you can imagine the robot has to pick up, move, and then place the bottle, and then we have to close our vise fingers. The third way that our robot can fixture the bottle is that it can use the frictional contact between the surface and the bottle. You can imagine how much frictional support that contact provides is a function of the surface. And so the robot can use different surfaces in order to fixture. So on the left, I show that it maybe is using a table, versus on the right, it is using a higher frictional surface, which obviously gives more frictional support. And so if we take all these fixturing methods, we actually only had to add 2 other operators, and I can get into the details, but the rest of the things are implemented by Fluence. Okay, so now we have our task defined, and we have our series of operators. And if we bring back to what we talked about before with the planning, that if our robot were able to generate the sequence of steps, which is our plan skeleton, you know, the sequence of operators, if it were to select that through, then this plan skeleton automatically defines what our constraint graph is. And here I've drawn a very simplified in cartoon picture. So how does our robot actually find this plan skeleton, the sequence of planning, and then generate this constraint graph? And this is going to take us to how we actually do this planning. I guess before we get to that, are there any questions so far? Okay, we can jump into planning. We're going to use, generally we're going to fall within the context of what's called task and motion planning, or TAMP. And very specifically, we're going to use a TAMP planner called Pedal Stream, which is the work of one of my lab mates. We're going to dive into the specifics of like how this TAMP planner works. As I mentioned, if we have time at the end, I can talk a little bit more broadly about task and motion planning and kind of what are the pitfalls of maybe this particular approach. But how does the one we're using work? So given a domain, we can sample a set of values of our parameters. So you might imagine that we have some set of graphs, and we can sample, what are valid graphs that satisfy our constraints. Given these samples, these satisfying samples, along with that operators that we've defined, a starting state, and some definition of our goal, we take all of this and we hand it off to, in this case, a PDDL planner. Specifically, we use fast downward. So that is a discrete planner that is going to search over different possible plan skeletons. What are the different sequences of steps that we can use? And these, credit to the AI planning community, they've developed really great domain-independent heuristics in order to be able to do this search very well. Once we found this search, as we've said, that automatically generates our constraint graph, and then we use the samples that we generated to check, do we have a satisfying solution? If we don't, we basically iteratively, we generate more satisfying samples, we use those samples to search again, and we basically keep going. Again, if we come back at the end, we could talk about what that guidance for that sampling is, but we're basically going to iteratively do this until we output a successful plan. A nice way to think about this, if people are familiar with a probabilistic roadmap, a PRM. So a PRM samples configurations in order to generate a graph and then searches that for a path. Pedal Stream generates samples in order to search over that graph in order to construct a plan. So it's the same kind of iteratively in order to build a graph and then in order to search. So that's the planner that we use in order to kind of search over what are satisfying solutions for this constraint satisfaction problem. And if we bring this all together, now we can actually appreciate what's happening in the video I kind of previewed earlier, where the robot is using task and motion planner, specifically Pedal Stream, in order to find a variety of different solutions given different environments while accounting for all of the force and motion constraints that we've talked through. So in some cases, it's using a vice. In some cases, it's using tools. I think it already walked through, although I can loop back. I can get that to play again. There we go. That we can see, for example, on the bottom left, that the robot first knows that it has to relocate the bottle onto a higher friction surface in order to get enough frictional support before it can first twist the bottle and then accomplish the rest of the task. And like these are 4 solutions to kind of show off the full glory. This is a combinatorial search space. And so here I've actually plotted the different push twist methods across the different fixturing methods to kind of give you a sense for the variety of the solutions that the planner can now find. And this is not even all of them. But this is what, by defining operators that we can now search over, this is what gives us the generality to be able to solve in a bunch of different environments. We've talked through all of this in the context of this one example in terms of like opening a childproof bottle. We've actually applied this to 2 other domains. So one other domain is we've gone back to twisting a nut, where now the forceful operation is that we want to exert a torque about our nut, and we give the robot the ability that it can either twist the nut using its hand or picking up and using a spanner, and that it can fixture the bolt the bar that the bolt is attached to, either by using a second robot to hold it in place, or the robot reasons over that it must pick up a heavy weight and put that down on the bar in order to hold it in place. And just like before, we can use PiddleStream to kind of search over what are all the different variety of solutions that the robot, or in this case robots, could select. We actually have a third domain that is still in progress. It's returning back to cutting. This is still very much in progress, but borrowing some of the assumptions from Yanbin Jia's group, who's been doing excellent work on cutting. We're thinking about cutting in the context where you consider that the object that you're cutting is a rigid object, and then parameterize the actions as two different forceful operations, where you first do a downward press and then a downward pulling slice in order to chop the object. But this is very much still in progress, and so I do not have videos of robots cutting potatoes yet. That's coming soon. So there's one last piece of this work that I want to talk about before kind of zooming back into the whole picture. And that's returning to this kind of point that I made in passing, that one of the fixturing methods is that you can use the contact between the bottle and the table. And how much frictional support provided is a function of what that table surface is. And specifically for the table that we have, the table by default for the amount of force needed to open this bottle does not provide enough frictional support, that this does not create a valid forceful kinematic chain. So this is why we saw in the videos that the robot would often either relocate to a higher friction surface, or it would relocate using the vice in order to fixture. Let's say we lived in some alternate world where someone came in the middle of the night and they swapped out my robot table, such that the frictional value was slightly higher, that it was just high enough so that now this frictional contact was stable. We've moved that wrench in ever so slightly, such that now is within the bounds that our frictional contact provides. Do we want to trust this? Do we actually want to use this frictional contact? I would argue no, because I would argue that it's incredibly brittle and that you're dependent on a very particular, in this case, value of your friction coefficient, which you should never depend on a particular value of your friction coefficient. And so how do we get our robot to have this kind of reasoning? How do we get our robot to basically be robust to the variations in these physical parameters? And the way that we did it as kind of a first step is that we took a bunch of samples where we varied kind of epsilon perturbations of our various physical parameters, of our friction coefficient, of our radius of contact, of our grasping force. And then we effectively counted how many of those under the variations are stable in order to give a probability of stability, which in this case is a probability of the success of our action, probability that frictional forceful kinematic chain is actually maintained. And if we take the negative log of the probability of our success, then minimizing the cost corresponds to maximizing the planned likelihood of our action. And it's actually very easy within our task and motion planning framework to integrate cost. And so if we take this cost that counts for possible variations in our physical parameters, that enables our robot to kind of make more robust choices. So in this case, given the choice of do I fixture using a vice or do I fixture using frictional contact, the robot can reason over based off that cost that it is more robust to use the vice, effectively because the largest forces that you are experiencing are now being maintained due to those kinematic limits, which are more robust than using frictional limits. In addition to kind of these more global choices, the robot can make smaller choices, such as given the choice between two grasps. By checking for that robustness and evaluating that cost, the robot can choose which is the more stable grasp. So this is kind of a very first step towards how do we get our robot to make more robust choices. So kind of bringing everything back and summarizing, in the second half, we saw how we can use a task and motion planning method that accounts for reasoning over forces and using more complex compliant controllers in order to generate a combinatorial number of solutions that enables you to generalize across those environments. So what I'd like to do next is I want to briefly mention kind of the ideas that we're working on now, kind of the ideas moving forward, and then probably break for questions. And then depending on time, there's some like algorithmic aspects of task and motion planning that I would like hope to chat about, but that is probably dependent on how we're doing on time. So briefly to kind of mention what we're working on now, there's kind of 3 things that I want to highlight. One is that first half of the talk, we use tool use as an application. And I think there's still a lot of interesting work to be done there. A lot of people have looked into tool use in the context of how do I extend my kinematic reach. And I'm more focused on how we can generally think about tools in order to amplify our mechanical forces. Second piece is that in that last bit, we talked about how to be robust to uncertainty in our physical parameters. And that is a first step. But I think if we're dealing with how do we plan and do control over these tasks involved forces, there's definitely a lot more reasoning that we could do with respect to uncertainty, right? I mentioned in response to Dan's question that we are assuming where all of our object locations are, which is anyone who deals with robots, like assuming you know where everything is perfectly is a dangerous assumption to make. So kind of developing more robust methods for dealing with uncertainty is kind of a must to get any of this to more realistically work, I would argue. And lastly, and honestly, the part that's taking up the most space in my brain at the moment is thinking about forceful manipulation over flexible objects. So far, all of our work has been focused on exerting force on rigid objects. And so the force is primarily used to actuate objects in relation to each other. But now if you consider objects that can deform, there's this really interesting relationship between force, motion, and deformation. And we've been looking to how can you expand task and motion planners and also in the context of multimodal motion planning to actually reason over flexibility within your objects. And it actually gets into the fact that you break the quasi-static assumption because you have parts that can actuate, and you have to reason over what forces do I need to exert in order to actuate them. And the example that has been keeping me up at night has been if you wanted a robot to insert a battery and like reasoning over how to plan and exert with that spring. It's a really interesting question, I think. So I think I'll break there for a minute and stop for questions.
I would like to ask a question. So Rachel, thank you for the interesting talk. I don't know if you mentioned this, but if you have, for instance, 2 robotic arms, that both of them need to twist something together, but in opposite directions.
Michal, you stole my question.
Yes, and this is
they need to cooperate somehow. Sorry for the noise here.
You're good.
So, do you work on this stuff as well? Have you thought about how to define the constraint graph in this case? Would it be different?
You have landed on. Sometimes people ask, like, your method can generate a lot of solutions. What solution can you not find? And you have given my favorite answer to that question, which is that as we've defined the task, and it's purely like how we've defined it, is that you are exerting a push and then a twist on your lid while holding the bottle rigid. Where a totally valid solution that we cannot find is if you maybe just push down on the lid and then twist your bottle. So if we wanted to be able to find that kind of solution, we would have to define our forceful operation a little bit more generally about, instead of just it being a function of the lid, that is a function of those 2 objects together. In that case, you then have, right now we have an uncoordinated bimanual task. If you were to do that kind of twisting, you would then have a coordinated bimanual task, where I think you would need an operator that reasons over the closed kinematic chain aspects of that. So it is a valid thing to fit within our framework because of the design decisions we've made. Our robot cannot currently do it. And you'd have to do a little bit more complex motion planning. So no, cannot currently do it, but it would fit within.
Thank you. One quick last question. Dror, please.
Yeah. So Rachel, first, thank you for this talk. To me, it was very inspiring. And I would like, if you can discuss a bit about the relationship between working in simulation and working in the real world, and how you chose what to do here, what to do there, how much of the, the conclusions here you can take to the real world, and how do you do the adjustments when you go from one to the other?
Mm-hmm. So throughout the talk, I think I only briefly showed videos of this going in simulation, and just for full transparency, in the first half of the work, the simulator that I was using was OpenRave, and in the second half of the talk, I was using PyBullet. But in each of these cases, I am purely using the simulator basically as a visualizer, because all of the kind of physics-related checks that you might imagine doing within a simulator are all done by our mathematical modeling, right? I am not running a simulator forward to seeing if the object slips out of the hand. I am using my analytical models to evaluate whether that is true. And so I am not relying on the simulator to check physics for me, which means there isn't an issue when I move to the real robot of like, who is now checking the physics. I will say, and this gets back to Dan's question from earlier, that there are certain things that you would have to transfer from going to simulation to the real world, which I do not deal with by assumptions of how I've set up my environment. So for example, I do not have to deal with the perception problem, because in the same way in my simulator, I know where all my objects are. When I move to the real robot, I tell it exactly where all of the objects are. So I've kind of made assumptions that ease what people would consider the sim to real problem. Additionally, the fact that I'm not actually using my simulator to evaluate physics for me. I'm assuming that I have the models to do that myself.
Okay, thank you.
Okay, thank you very much, Rachel. Let's